There are no questions, let me start from where I left off last time. So we saw an implementation of the linked list data structure as implemented by ADTs in Python. Methods in list data structure implemented as an ADT. Correct. Now you can define. You can also define this. For example, if you have a list L, a Python list, then you can say L of I. Ith element of list. And if you can also define a function that that gives you this value in your linked list data structure. So you can say something like, you can define a method which is something like def. So this is inside the class definition. Class my list or whatever, my list, correct? Or we were calling it a node. So class node, and you have defined a function called init, and so on. I will not go into these definitions. After these, you define something like value at self, comma I, and now you just go through the list iteratively or recursively and return the value or at I. Correct? Is it clear? So how do I do this? So our convention was if self dot value is equal to none, then what do? Then you should raise an exception or something, correct? Or return none or some such thing, correct? Depends on your implementational decisions. So for example, if you are returning just none, correct? The self dot value is, then you just return none. Correct? If self, if I is equal to 0, return self dot value. And returning the recursive version, you can write the iterative version also. Self dot value, okay. And now, if I is greater than 0, then what do? If I is greater than 0, of course, if it's less than 0, then it doesn't. So you can extend the minus from the end and so on. I will not go into that. So if I is greater than 0, then what do? You return self dot next dot value at I minus 1, and finally you return none. And you can reorder these to make it more efficient. Correct? Do you get my point? This is just some sample code. Correct? Now you can also write a code for slices. I invite you to write a code for def slice self comma I comma j, and you can write the code for that. Correct? And even here you can handle handle negative indices, where you have to go to the end and then come back. So you cannot really write recursive code, or can you? I mean, so from the length you can write, and so on. So I will let you think about that. And slice, similarly, you can return the slice I colon j. Correct? Okay. Whatever. And now a bit more about these classes. So we saw a reserved keyword, which is this init. Correct? This is used in only a particular sense. It is a keyword. Similarly, there are other keywords that you can use. Okay, redefining them has a specific meaning. So, for example, you can def string str. And what does this do? This should return a string implementation, a string version of your list. This should return a string which is somehow related to your list. Correct? Returns a string implementation of list, or of list. Correct? So how would you implement it? So again, the implementation is simple. You can just, if self dot value equal to none, return the empty string. Else, if self dot next equal to none, return str of self dot value. Correct? So this str, assuming you are storing integers or strings or something which can be converted to a string, you use the underlying function str, which we are defining in the case of nodes here. Correct? And else return something like self dot str of dot value plus comma plus str self dot next. Correct? Are you with me?
Sir, so can we use this function for any class like?
Yes. So in any class, you can define this underscore self underscore str self, and then whenever the function, so suppose you define it in a class C def str self, then when you call and you have a val is equal to C, you initialize it to something with in the class C, then you can say str val, and this function would be the exact function that we called. Correct?
So what will be the return value?
The return type will be a string.
Okay.
What do the underscores around str mean?
The underscore around str means that it is a reserved keyword. It is used only in a particular way. So basically, you don't call it by saying, I guess you can still call it by saying uh, val dot str underscore underscore str, something like this. But the alternative syntax is you just write str val and this underlying function will be called.
So could we define it just as def str without the underscores?
No, you cannot, because you are calling it, you don't want to call it by the usual access method of val dot underscore underscore str underscore underscore. You want to call it by giving val as a value to str. So it's like, do you understand the difference? So I want to say, and why do you want to do that? Because str is a function that is often present in many classes. I mean, it is the usual way to convert uh, an object to a string, to get a string representation for an object.
Sir, like str function is already present in Python, right? So is it like we are extending that for our class?
Mm, internally, this underscore underscore str will be replaced. When you call str, this function will be called. So maybe it is via overloading this or something, or by extending this. But the resulting effect is that you define this function and this function str will be, and you call str, then this function will be called. Correct?
Okay, sir.
So is it
Okay.
supposed to be like a static function?
It is like a static function. Yes. It is a static function. Yes. So there are other special functions like you can say underscore underscore add.
So, so sorry, I didn't understand. I don't understand the difference between put like adding the underscore and not doing it. Like, what's the difference? Could you repeat?
So you never say, you usually don't say val.str. You cannot say val.str empty. This is wrong. You give str a value, which is of this class C.
Okay.
So it's like a static function. So like somebody correctly pointed out, you it is a function of um, which is a class function, which takes in a value and you get a string out of it. It's
So
not
why?
you are.
Okay, sorry. No, why is val dot string wrong? Like, what is wrong about it?
Meaning that's not the usual syntax.
Okay. Okay.
So I guess I'm not 100% sure, but you can try. Can somebody try right now? Does this work? You can, I guess, say this.
Yes, sir, it works.
Okay. So if it works, then that's good. But definitely str val will work. Correct? So this is a kludgy notation. You just want to do a clean this thing. And this str is used in many other places. So that's why. Correct? Similarly, add, you can do, so if you have this in a class C, correct? And you define an object O of O is equal to C. And now you can say O plus val. And this add function will be called. So this infix thing, so basically it makes it, so maybe that is an advantage in string also, it makes it infix. I mean, it makes it, so it's more evident in this plus that you want an infix operator, correct? You don't want to write O dot underscore underscore add val. Rather than that notation, you would like to write this. And the way to do that is to define this function add. Correct?
So I didn't understand how are we defining that part.
How are you defining this add?
Yes, sir. O plus that part.
So you can say, for example, in your def, you can say add self. I'm defining this in the node class node, correct? Self dot val, and this has the effect of suppose you define it so that you do return self dot something like self dot append append val self dot up, or that's not a good way to do it. So you can create a new list and add val at the end. So this is kind of making a copy of this object and appending val, or whatever meaning you attach with this plus. You get my point?
Okay, sir.
So whatever meaning you attach with this add, whenever you call O plus val, the function add will be called. And the value that is returned by this function will be returned. Do you see my point?
Yes, sir. Yes, sir.
Correct. And in usual this thing, for example, in lists also you can say L is equal to 1 plus, correct? So in, for example, my list, you can say in node, you can assume that this is also a node, and you can concatenate the list. This add means concatenate the list. And if you want it to be not in place like lists, correct? Then you can create copies or something like that, correct? So whichever way you want to do it, correct? It's in your hands, correct? Okay, that said, one more thing about this is that if you define this add function, O plus val and val plus O have different meanings. This means you are calling the add of O, and this means you are calling the add of val, which may or may not be defined. So this plus is not necessarily commutative, correct? Like in lists. Here it is well defined, but you could also, for example, I mean, you can define this L is plus 1 and add an integer to it. And what does that mean? You have to interpret it in your add and implement it appropriately, correct? But by definition, these two are different. And one of them may not be defined. If val is, for example, an integer, then val plus O might not be defined, will not be defined. Correct? And there are a bunch of other such things like add. There is underscore underscore equal, which returns a boolean, which is supposed to return a boolean, which is used for equal to. There is less than, which is used for less than, and so on. And you can look up the documentation to see what are the operators that are available, correct? And which you can define this way, correct? Are you with me?
Yes, sir.
Sir,
Okay.
I had
tell
a
me.
small question. If I want to overload add in some way so that it does one thing when given a string and one thing when given an integer.
Yeah, you can do that.
How exactly, sir?
So there is a, I believe there is a function called type of.
Oh, okay.
Which you can use.
Okay, got it, sir.
And you can look up the definition of that, correct?
Yes, sir.
So you can get the type of the thing and then you can. Yeah. So, yeah, one more thing. So far we did this implementation of node, correct? We said, we defined this class node and we said that for inserts, we have to do replumbing. Do you remember that if you want to insert in front of the list, you'll have to change the self pointer, which you cannot. Therefore, you have to do replumbing. You have to insert it between the first and the second, or 0th and the first, and then exchange the 0th with the newly inserted. Correct? Do you remember? So, replumbing or rewiring can be avoided if you use two-level hierarchy. Of so what do I mean by a two-level hierarchy? I mean you define your node class. So you define a class called node, but that is not the class at the top. User doesn't see a node. It's used for an internal storage, and instead you define the class list or my list, whatever, my list. Correct? And in my list, what you do is you keep a pointer. So the def init self comma val would be just self dot head is equal to node with val. So let me do the more general thing. Val equal to none. Correct? So now you know when. Okay. So now you're so basically you have a big block inside which you keep this. So this just contains, this is your my list, and this is your node. And inside this, in the head, you store, so this is the head pointer, and here you store the head of the list. And then you build the list inside this. And now you cannot change self, but head you can change. Correct? So it is a one level indirection in this. Do people see this?
Sir, self points to my list.
Self points to, yeah, the external self points to my list. I mean, okay. In my list, self points to my list. In node, the self points to the node. And here, I mean, if you want to, for example, let me show you how to do insert. Insert self comma val. Correct? So if self dot head equal to none, then self dot head equal to node val. Correct? And now it's not none. So what do? Self, temp is equal to node val. Correct? And then what do? You splice it in the beginning. So you say node, sorry, you say you attach the list temp.next is equal to self, head is equal to self.head, correct? And then you change self.head to be equal to 10. Correct? So do you see what happens? So there is this big box which is my list, and there is this small box inside this which is pointed to by head. My list just contains the head. It's a dummy this thing. It's just used to store the head. And after that, the list is stored inside the node data structure as usual, correct? But when you want to change self, you know, I mean, it is via this head that you change it. So you, because head is stored inside my list. Do you see? Is it clear to everybody?
So I don't understand how this is. I mean, like, okay, I don't understand this. Could you explain why this is different from replumbing?
So there are two classes. One is node, and the node contains again an init, def, init, something, correct? You do not define, so you can define delete and so on in, you will have to define delete here, but don't define insert here, correct? So you never insert inside this node. What you do is you just yeah, so you change the so you change the so what was the problem we were having in the self thing? We had a one level indirection, and you could not this external self. Now you store this pointer as head, and now you can change head. The head is just stored inside my list, and you can change its value. So previously head was pointing here. Now you remove it and you appoint it here. Attach this node, correct?
So why can we change it now and we couldn't do it before? I don't understand.
Because head is a variable that is a name that is stored inside my list. You are not changing the self of my list. You see, you're not changing the self, you're just changing the thing stored inside self, which you could, which you can. Previously, you had to change self. So there is a two-level indirection. First, you go from self to head, and then from head to the actual list. It's as if you have cached the self in this head variable. Is it clear?
Yes.
Okay. And the delete and so on are similar. I would write them because they just call the delete for the mylist delete just calls the corresponding thing for node and just adjusts the base case where the list becomes empty. You just set head to none if there is just one element in the list and you delete it, something like that. Correct? So in some sense, this is more complicated, but in the other sense, it's cleaner. So you don't have to do any replumbing. Correct?
Yes, I have.
Okay, good. Okay, so now we move on to a different, so an extension of lists, which is trees. So we are going to talk about trees a bit. Okay. So what we are going to talk about is binary trees, usually. Correct? So first, let me, so you are doing discrete math concurrently with this course, correct? If I'm not wrong.
Yes, sir.
And you must have seen graphs there.
Yes.
Have you seen directed graphs and trees and what have
yes,
you?
sir. Not
Okay.
trees.
Huh?
Directed graphs.
You're not
Not
seen trees yet?
Yeah, I think so.
Okay.
Only directed graph. Trees were introduced in Haskell at the end of the semester.
Okay, fine. So you know what trees are, correct? So what are trees? Trees are, so trees can be of two kinds. So trees are graphs in which are acyclic graphs. So a tree is an acyclic graph, correct? Now you can interpret, so this is in the undirected sense. There are no undirected cycles. Okay. So an acyclic graph which is connected. Of course, without connectivity, you will not get a tree, correct? So I draw a tree. You can draw a tree like this. You have these nodes which are connected by edges, and you can think of these also as directed graphs. So what do I mean by directed graphs? Each edge has a particular direction. Okay, and every vertex has a unique parent. So this is a vertex V. This is the parent of V. This is a vertex V prime. This is the parent of V prime. And these two are equal in this case, correct? And there is only one vertex in the tree which does not have a parent, that is the root. So this is the root. And all the edges are directed towards it. So I'm doing this in a very informal way. You will do it formally in graph theory, I guess. So is the notion of a directed tree clear? So a directed tree, firstly, is the notion of undirected tree clear? That's not a good question to ask. Is there anybody who understands the notion of directed tree? That's also not a good question to ask them. So, well, let me just say
so
this.
Underlying graph is directed. That's it.
The underlying graph is, there is no underlying graph.
Not connected, direct. Sorry.
No. So the underlying, what do you mean by the underlying graph? Are they non-tree edges?
And as a tree is an acyclic graph, this graph has to be direct for a directed tree.
No, the underlying graph is undirected. There are no undirected cycles. For example, this is not a tree.
Okay, any path has to be like have in the same direction.
Yes. So
okay,
every node path.
Yeah, in number of in nodes equal to number of out nodes except the root and the last leaf and the leaf.
And the graph is the underlying undirected graph is connected because correct.
Sir, can you explain what a parent of a parent means over here? Like,
so parent just means that there is a special node. Every vertex has out degree 1. So there is a special node parent of V which is associated with the vertex V.
yes, sir.
And there are no cycles, no directed cycles. So these are all equivalent definitions, but I don't want to preempt what you do in discrete math. So such things are not permitted. Correct? By the way, who's teaching discrete math? KV, is it?
No, Professor
Professor
Partha.
Partha is teaching. Okay.
and Ramya.
And yeah, Ramya. Yeah. Okay. So, so you have the parent of every vertex, and there are no directed cycles. The graph is connected. So many of the so let's say let me give a formal definition of directed tree. For all V in V, there exists a unique path to root R, correct? And even that is not sufficient. So, well, let us say, yeah, and no cycles, no directed cycles. Okay, so for us, we will think of a root, and then it has. So here I drew the parent as a parent pointer. What we are going to talk about is trees where the number of children of a node is bounded. What do I mean by that? What is the child of a node? All those nodes which have V as a parent are the children of that node, correct? So for us, trees will look something like, this is where the number of children of a node, this is usually called the order of a tree. So this bound is called the order of the tree, correct? For example, in a binary tree, you have the root. This has at most 2 children. And then each one can have at most 2, maybe just 1, maybe 2, maybe none, and so on, correct? So this is an example of a tree. Is it clear? And the parent pointers are the reverse of these child pointers. So if, correct? Am I making sense?
Yes, sir.
So, for us, we will deal primarily with binary trees in which the bound of 2 children on a vertex, correct? There is a bound of there exists bound of 2 children on a vertex, correct? And we will represent the 2 children. We'll give them names. We'll call them the L child or LC for short of V, and R child, left child, and right child of V. Correct? And so the way we draw a tree is we will draw a tree from top to bottom, with the root being at the highest, at the topmost node, and the children being drawn below, correct? This is just a representation. It's often convenient to do it this way, and in sense for directed trees, binary directed trees. You will see more generality in graph theory, correct? Okay, so having said that, what is the use of trees? So for that, if you think of the linked list can be, what is a linked list? A linked list is you have a node and this has a value and a next pointer. So it's basically, in graph theoretic terms, it is a path. There are no cycles. You cannot have the last thing coming back. That's a circular list. We don't allow that. We just paths, which are special kinds of trees in which there is exactly one child. Do you see my point? So if I drew it vertically, I would draw it like this, correct? You can think of this as the root and the order is equal to 1. Every node has at most one child. The last node does not have children. It points to none, correct? So a binary tree is a natural generalization of this, where you have a value and an LC and an RC, a left child and a right child. And there's another value and there's a left child and maybe no right child. So none, and so on. Correct?
Sir,
Value, tell me.
you said binary tree is a generalization of something. What was that something?
That is just a linked list.
Okay.
It's a generalization of lists.
Yes, sir.
Because lists are just structures in which the out degree is 1 and there are no cycles. Here the out degree is 2 and there are no cycles. Correct?
Yes.
Okay. Now, okay, we have defined these fancy data structures. We have made the degree 2 instead of 1. How does that help us? So unless there is some correlation amongst values, this is not much use, correct? And what is the correlation between values? So we talk about binary search trees. Okay. So in binary search trees, the self dot value is less than self dot r child dot value and is greater than self dot l child dot value. Basically, the value of the left child is always lesser and of the right child is always greater. And now by induction, you can show that all the children on the left of this will have a value which is smaller than this, correct? That's not true. I'm lying. So, but so it's more. It is. So this is of course true. But what is true is that everything on the left has a value which is smaller than the value of. So anything reachable from the left pointer has value which is smaller than the value of self, and everything which is on the right has a value which is larger than self. And why was I lying? Because this, for example, if you take something like 5 and you say this is smaller, correct? 2, and this is larger, 6. But this is not a binary search tree. Correct? Why? Because the 6 is on the left of 5, but it is larger than 5. So here what is allowed is 5, let's say 2, and then 4, and here 1. Correct? So all the children, so the invariant we maintain in this tree is that all nodes to the left, so all the left descendants of so any descendant of the left in the left tree, or any node in the left subtree of self has a value less than self.value, and this is less than value of any node in the right subtree of self. Correct? Are you with me?
Yes.
Okay. So remember, this is wrong. Correct? This is wrong. This, I should point out, is wrong. Correct? So this alone is not sufficient. I mean, it is correct, but it's not sufficient. We need this is the correct property. Correct? This entire property. Okay. Having said that, so we have put some arbitrary restriction on, seemingly arbitrary restriction on the values. How does that help us? So it helps us because how would you search for a value? So so let me create a tree. Let's say 5, 2, 1, and now this is 4, and this is 3, something like this, correct? 8, 6, and let's say 9, correct? Now I ask you to find the value 3. So how will you do that? So in a linked list, you went sequentially through the list and searched for the values. Here, you go to the root node and you check whether the given value is less than or greater than, whether you have found the value or the value is less than 5 or greater than 5. So in this case, you would know that the value is less than 5. You're looking for 3, correct? So you have to go this way. Now, at this point, you know that the value is greater than 2. So you go this way. And here, you know the value is less than this thing. So you go to 3. Now, how many nodes does this tree have? It has 4 and 3, 7 and 1, 8 nodes, correct? Correct? There's no 7. Yeah. So it has 8 nodes, but we had to search only for 3 these things to find the value. Okay, you might say that even if I had stored this as a linked list, 1, 2, 3, I would have found it in 3 steps, correct? But what about 9, let's say? So to find 9, I will require 2 steps in this, correct? I will check, is this greater than 5? Yes. Is it greater than 8? Yes. And I will reach 9. In 2 steps, I would have found it. But in the linked list, I would have to scan the entire list to do this, correct? Do people see this? I guess you've seen this.
Yes, sir, we have seen this.
Okay, fine. You've seen balancing there also? Have you
Yes.
seen balance?
Yes, I think so.
Yes, sir.
Okay, fine. but let's do it all the same in Python, correct? So, the point is just this, that the number of accesses you need to the value is proportional to the depth of the node you are searching for in the tree. What is the depth? It is the maximum distance of a node from, so depth of a node is the distance from the root through a directed path. So if you're searching for 3, the distance is 3. If you're searching for 9, the distance is 2. If you're searching for 6, the distance is 2 in this, correct? So the worst case, and we will define this later in the course, but intuitively the time to access a value is equal to the, or is proportional to the number of to the depth to the is less than equal to the depth of the tree. Now, why would so and why should the depth of the tree be small? Is there any reason why the depth of a tree should be small? Consider
It's
this.
log n if it's balanced.
If it's balanced. If it's not balanced, the tree might be very skewed. And then you would be, so if you have a right skewed tree, say you have 1, 0, sorry. So you have 0, 3, 5, 7, 9, 11, 13. I'm just drawing some 2, 4, 6, 8, 10. This is a valid binary tree, correct? A valid search tree. But you are taking roughly linear number of steps. So steps which are proportional to the value of the node, correct? If there were 100 such nodes, you would, if the depth of the tree were, so if it stored till 100, the first 100 values in a completely right skewed tree, the depth of the tree would be 50, correct? Do you agree? Or around 50, maybe 50 plus 1 or something, 51 or something, correct?
Yes, sir.
So 0 to 100, sorry. So whatever. So that would defeat the purpose of the tree, correct? That you just cut down the running time from n to n by 2 at most. The worst case running time previously was n. To search to the maximum element, it took n steps. Now in this case, it is taking something like n by 2, and maybe it's even n. This is also a valid tree, correct? Here you are taking all the way up till 100. So the power of these search tree comes from the fact that you can balance them, keep them balanced, correct? And we will show that so intuitively it is clear that the depth of the tree is proportional to so of a balanced tree grows like log of the number of nodes stored, correct? If it's a complete binary tree, you know that there are something like 1 plus 2 plus to the h many nodes at depth h, correct? So this is 1, this is 2, this is 3. So 1 is 1 node at 2 to the 0. So that's 2 to the 0. And then, so what is this? 2 to the h plus 1 minus 1. And so it's, this, if it's a complete binary tree, then this is, if this is n, then h is equal to n plus 1 log of this minus 1, something. Correct? It's roughly logarithmic. And this should remind you of something that we did earlier. So what did we do earlier that this should remind you of? Anyone?
Binary search.
Binary search. Very good. So binary search is, so this is just some sort of crystallized binary search. You're doing, you're storing the items in a way that all the binary searches are crystallized into one this thing. So basically, you're so if you are looking at the what is called an pre-order of in order of this tree, then you will see that it is a sort list. Correct? So you go from no, sorry, you do what? Which order is it? In order. Correct? So you do 0, then 1. From here, you do 2, and then 3 and 4. So you follow this path, and the order in which you first see, so you start on the leftmost, this thing maybe. So you start from here, and you see the
Sir?
the first. You see them in order, basically. Yeah, tell me.
Sorry, what's the definition of in order? Like,
The
is there
definition of in order is you see self dot. So self dot value, basically what I wrote here. So let me write the definition, formal definition. So if I do in order self, correct? So in order self, suppose it returns a string of things in, or list of things in the in order value, then this is just if self dot value, if self dot, so basically if self dot is empty, return the empty list, and otherwise if self dot self dot l child, self dot l child equal to none is, sorry, equal to none, then no, I should do it the other way around. Is self dot ret is equal to, so let me define ret is equal to this, and the return, I should not have done this, but anyway, ret is equal to self dot lc dot in order and then ret is equal to ret plus self dot value, and then ret is equal to ret plus self, bad idea to do this way. No. Oh. Okay, so let me put it like this. That is a little better. So this is the formal definition of input. You do the left child first, the in order for the left child, then you do the current node, and then you do the self.right child.in. And I just got bogged down by details in, yeah, so tell me.
Yeah, okay, sir. Thank you.
Correct. So,
So shouldn't you be adding each node to red instead of reassigning red?
sorry, I missed it here. Yeah, that is correct. The first time it was fine because I just had to overwrite it. If you want to be more this thing, you can still do it because the only thing, yeah, correct?
Yes, that's fine.
Okay. So, so now,
Sorry, so what have you? Sorry, what have you added? Have you added red again there on the right side?
yes,
Okay.
I have, let me do it clearly. And let me just remove it from here. If you want, you can add it. It doesn't matter because before this, it is just the empty list. So if you want uniformity, you can do it here. Is it clear?
Yes, sir.
Okay. But what does this buy us? So in order of a binary search tree is always a sorted list. Okay. In order, if you have a binary search tree and you do in order on that, you get a sorted tree, a sorted list. And now if you want to do binary search, you can think of it as so if you maintain the tree, so think of it this way: you have this list and you have this array or whatever. Let's think of it as a list. This is your in order list, correct? This is what you get out of in order, and you have a tree over it. If the tree is balanced, then whatever you run is a exact binary search. Otherwise, if it's imbalanced, then it's not binary search, but it is a search, correct? Do you get my point?
Yes, sir.
So it will still produce the correct answer, but it would take time proportional to the height of the tree, correct? So we will make this more precise later. But how would you write search? So if you write one routine, then it is all these routines are very similar, correct? So how would you write search? What does search do? Returns self comma v, returns let's say true if v is in tree and false otherwise. So how would you write search? How do you search for a value v in the tree? So first again, so it is basically very similar to what I have written here. So if self dot is empty, and I have not defined what is empty is, it is like the usual it is like, so I should have also defined, of course, the init. So def init or self, which would just be self dot. So it is just like the u is equal to none self dot value is equal to val, self dot lc is equal to self dot rc is equal to none. Correct? So maybe you should write it like self dot lc is equal to none, self dot rc equal to none. Positive space, I wrote it like this. Correct? So these lc and rc are the two children. Correct? So if self is empty, how do you write self dot empty is empty?
Self dot value equal to
is equal to none. So def is empty if self dot value equal to none, return true, or more simply return self dot value equal to none. Correct? So if self dot empty is empty, then what do you do? Then you return false. And if self dot value equal to v, which means that v has been found, return true. And now if it is not the case, if self dot value is less than v, self dot value, v is less than self dot value, so v is less than self dot value, then what do? You go left. Correct? No, sorry, what am I saying? Yeah, if self dot lc is not equal to none, then return what do? Self dot lc dot search v. Correct?
Yes, sir.
Else if self dot rc is not equal to none, return self dot rc dot search v, and then finally you return false. This will catch the two cases where the else of this, you can also say else return false. Correct? And you can say this, you can move this return false inside. So there are many variants, you can write it any which way you want. Correct? This is also fine. And now along every, if you have returned something, so you don't have to return globally. Every case is considered. Correct? Are you with me?
Yes, sir.
So this is very simple. Notice here we are doing this less than, and we are assuming that these two values are comparable, so that in the tree you stored the same type of object. It is all integers, or at least two things which are comparable. Correct? Two values which are comparable. If that is not the case, there will be an exception raised. Correct? So we have done find. Now, how would you do insert?
Sir?
Tell me.
I have a question for that. Could you explain the diagram once? You said something about if it's no, like up, sir. Yeah, the top. Yeah, this one.
This one?
Yeah. You talked about balanced trees and something.
So I said, if your tree is balanced, then that corresponds exactly to binary search. So any value you search will take log n steps, order log n steps. I mean, so suppose if your array is of length 2 to the t minus 2 to the h plus 1 minus 1, correct? And you have a complete binary tree of height h over this. So, correct?
Yes.
Then you would take exactly h plus 1 steps, which would be what you would take even in binary search.
Yeah. Okay.
On the other hand, if your tree is skewed, then you will take more steps. If it's very skewed, you can take as much as linear number of steps.
Yeah. Yeah.
So you would try to make the tree as balanced as possible in order to consume less time, correct?
Yeah. Yes, sir.
That's all I wanted to say there. So let me do insert and delete next time, correct? There isn't much time. There are just 3 minutes left for this thing. So tell me, are there any questions? No questions?
So we will have to, like in the isempty, we'll have in the argument we'll have to write that self inside it. Otherwise, it's showing error.
Sorry, I couldn't understand.
In the isempty, in the def isempty, the last program.
Last program, fine. Yeah. No, which one? Last program was fine. No?
Last program, the def is empty. The list is empty or not. So, yeah, here. So we'll have to write the self in the argument of the function. That is empty self equal to return self. Like I mentioned that in the comment. It's shown.
Oh, self. Sorry. You
okay.
Point.
Yeah, sure. Thanks.
Yeah, that's true. More questions, comments?
Sir, can you please scroll up a bit?
Okay. Tell me when to stop.
Sir, stop. Sir, a bit down. At the beginning of the last program.
Beginning of the last diagram?
The last program. The in order one.
Oh, the in order.
Yes, fine. Yes, it's fine, sir. Thank you, sir.
Okay.
Okay, sir. Thanks.
Okay. So, yeah, so that's all for today. And we meet again on Thursday, correct? And we will have a quiz maybe next week. Yeah. Correct? And how was the assignment? Any comments on the assignment? No comments?
So will they be graded immediately or later?
Huh?
Will the assignments be graded immediately or later?
Not immediately, I guess. It will take some time.
I had a doubt in the first question of the assignment.
Okay. I don't remember the first question. You will have to remind me what the first question was.
Just 1 second, sir. I'll just. The question is: the n people are standing in a circle numbered 1 to n. Control of the game starts with person 1. Person 1 eliminates the person at distance 1 to his left.
Okay.
And then the control goes to person 2.
Correct.
Yeah, and then person 2 kills a person distance 2 to its left. and then goes to the next person, and so on and so forth. It's not exactly the Josephus problem, it's modified Josephus problem.
Is minor variant of that. Yeah. Correct. So what was the question?
So I wasn't, I mean, out of the 4, I wasn't able to solve this one. I did the other 3.
Okay.
So, I mean, if you could give hints so that I can at least like solve it, even if I don't get marked for it.
Okay. Meaning, okay, let me do this next time. Okay. I just don't want to start writing code anyway. It's beyond this thing, correct?
Okay, sir. Okay, sure.
Okay. Thanks. Bye.
Thank you, sir.